Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a pleasure to have Laci Lovas give a talk. I don't think he needs much of an introduction. Everybody knows him. Those who don't know him, maybe the best thing is to say everybody wants to claim him. The mathematicians claim he's a mathematician. The combinatorialists claim he's a combinatorialist. We claimed for a long time that he's here, and his university in Budapest claimed he is there. And I think he finally avoided that by getting a lot of work and becoming chair there. So now, unfortunately, we can't claim he's here anymore. But we're very happy that he's here over the summer.
Thank you very much. It's a great pleasure to be back, and also a little bit of sadness that it was really great time for me here, but other tasks were awaiting me. But it's very nice to be here for a month. So I would like to talk about a topic that grew out, or it's part of a bigger project that has been going on here while I was here, and worked with Christian, Jennifer, many other people. Some of it will show. So this is a particular question is about which graphs are extremal graphs. So let's look at a sort of typical graph theory problem. Given the number of nodes and the number of edges, what is the minimum number of triangles? So which graph has the minimum number of triangles given the number of nodes and number of edges? I'll try to explain, because I think I would like to explain what the answer to this question is, because it will motivate somehow what the kind of questions I will be talking about. So this picture is the following. On the horizontal line, I consider the density of edges. So number of edges divided by n choose 2, where n is the number of nodes. And on the vertical axis is the density of triangles. So out of all triples, what fraction is a triangle in the graph? And now every graph then gives a node, so you get here a certain countable set. And this is what I've shown here is sort of the closure of this countable set. So of course, these are all rational numbers, for example, but so if I take the closure, and it looks like this. Now let me explain what various parts of this come from. So there is an upper bound, which is actually it's the opposite of the question that I asked. What is the maximum number of triangles with a given number of edges? And that is a special case of a classical theorem called the Kruskal-Katona theorem. And it tells you that this is the x to the 3/2 curve, and that it's always below that. And also there are, it's easy to see, just complete graphs with isolated points give an everywhere dense set on this curve, or arbitrarily close to this curve, I should say. Now, the fact that up to 1/2 you can get 0, of course, because you can have bipartite graphs up to this density. The fact that above density 1/2 you get something positive, it's a theorem which goes back to about 100 years ago by Montel, but in a more general setting, not for triangles, but for every complete graph. It was proved by Turan in the 40s. And so that theorem says that from here on, everything is positive. Now you go on, and we drew here a parabola that goes through origin and the 1/2 here and the 1 point there. And Goodman proved in the 50s that the every possible point is above this parabola. And in fact, there are infinitely many points which are on the parabola, 1/2, 2/3, and so on. So these are complete multipartite graphs that realize these points, and these are on the parabola. So there's an infinite number of points here on the parabola. And the question is what's happening in between two of those points. And sort of, even though it's not hard to see that you cannot have equality, the expectation was that you can get arbitrarily close maybe to this. But that was disproved by Bolobash, who proved that actually if you draw the chord between two of these consecutive points, then it will be above this chord. So actually it's kind of concave between two of those. Miki Simonovic and I wrote a paper in the 70s where we formulated a conjecture for how this curve looks like. And I will get to this. I don't want to state some kind of cubic curve that describes this. And we proved that in some neighborhood of these points, it's actually true. So there was some explicit number larger than 1/2. So in between, the truth is this cubic curve. And we conjectured that the cubic curve was true. And then in the 70s, or late 70s, Fisher proved that indeed our conjectured curve was the truth for the first of these intervals. It's a nice proof, but didn't go extend beyond these. And I'm happy to report that the question is now settled, and Razborov proved very recently that indeed the conjectured curves are the truth. So it's a strange shaped domain which has convex and sort of concave curves, but arranged in this same way. Now this is now complete. So we know that that's not hard to prove anymore, that everything inside this domain is actually realized in the closure. Now, what are these curves? And so this problem, it turns out that things are easier to formulate, remember in particular, when I tell you what the extremal graph is. So which graph realizes the minimum number of triangles. And this Manta result really says that if m is n²/4, then the only extremal graph is the complete bipartite graph, which means that if you go above this, then this has 0 triangles, but if you go a little bit above that, then you will have positive number of triangles. Goodman's result implies that for special values of this form 1 - 1/p times n²/2, the extremal graph is a complete multipartite graph with equal color classes. And let me ignore the divisibility questions here for n. N is very large. Usually that's the case. That's what's interesting. And Razborov result says, and this is the way it's easy to remember, that in between, the extremal graph is still a complete multipartite graph with appropriate p color classes, 2 of which are different and all the others. I mean, there are 3 possible sizes, and 2 of them are equal, or 2 of them are, so 3 different, but p minus 2 of them are equal. Now, the question is, what do we know about these alpha, beta, and gamma, about the sizes? So first of all, of course, we know that the total size is 1. 1 times n, and by counting the edges you get an equation. Doesn't matter, some sort of equation, quadratic equation on alpha, beta, and gamma. And of course you have 3 variables and only 2 equations, so this is still not uniquely determined. So you have to write up the number of triangles. It will be a cubic function, you differentiate, compute, and then you get some formula if you really want to know. But I think in this form, knowing what the extremal graph is really the crucial point. From then on, it's really boring. So this is a very nice result, and it closes up this thing. Here is another. It's an old result. Oh, sorry, that's 206 is a mistake. So that's an old theorem. I don't know why is it there. It's anyway. So there's the Erdős-Stone-Simonovic theorem from the 60s, which says that if you ask the following question, you exclude certain subgraphs. So you look at graphs on n nodes which do not contain certain given specified f1, fm. You want to, oh my goodness, we want to maximize the number of edges if you exclude these. So you are interested in the minimum number of edges which force one of these. So you want to maximize the number of edges in a graph with these excluded. Then the extreme graph is still the same as for a complete graph asymptotically, namely a complete multipartite graph with equal color classes, where this number of classes is the smallest chromatic number minus 1. So again, it would be probably more difficult to tell exactly, but asymptotically the extremal graph can be understood. Let's look at one more example where the answer will be a little bit different. So suppose, again, given the number of nodes, number of edges, we want to minimize the number of quadrilaterals in the graph. Yes?
In the top, when you said you have excluded subgraphs, you want to maximize number of edges?
Yes, I want to maximize. I apologize. Somehow this slide, apparently I was asleep or something. It's several mistakes. Yes. So suppose now we are given number of nodes, number of edges, and want to say minimize the number of quadrilaterals. Now it turns out that asymptotically number of quadrilaterals has some bound like this, and actually it's easier to remember again the extremal graph. The extremal graph is random. So asymptotically, the random graph has the smallest number of quadrilaterals. So after all of these,
One needs some mutable, no?
sorry?
If it's sufficiently dense.
Yes, I mean yes. So I'm assuming that it's sufficiently dense. Yeah. So I will always be talking about graphs which have a constant times n squared edges. So the number of edges, so dense graphs, and then this is true. So the question is, can we say something in general about what types of graphs can be extremal graphs? So what kind of So we saw a random graph can be extremal, certain multipartite graphs can be extremal. What other kind of graphs can be extremal? Maybe if we understood in general how extremal graphs look like, this could help with certain extremal graph problems, because we knew what to expect. So in order to formulate this question, I need to make a little detour and talk about limits of graph sequences. And this is joint work with many authors who are well known, and some of them are sitting here. And so let me give a quick introduction to this topic. So first we have to define Hom of GH, which is just the number of homomorphisms of a graph G into H. A homomorphism is a map that preserves adjacency. So this is a number. We'll be more interested actually almost all the time in this normalized version of it, where we divide by the total number of mappings from the vertex set of G to the vertex set of H. So this can be thought of as the probability that a random map from Vj into v of g into v of h is a homomorphism. Now, a sequence of simple graphs is called convergent if for every fixed simple graph f, f should be here, it is convergent. This is convergent. I don't know what happened here. Some mix-up, sorry. I think this should be here. No, I don't know. Some mix-up, sorry. So for every simple graph f, this density of f in Gn is convergent. So has a limit. Now, it turns out that there are, for example, random graphs are obviously convergent because with probability 1, because the density of anything you can easily tell what it should be in a random graph. And there are many other examples of convergent sequences, and I don't have time to talk too much about that. But I will, so if we call it convergent, it should mean that it has certain limit. And in fact, you can describe the limits, and it turns out that limits have a nice description in terms of we look at two variable functions defined on the unit square, which are symmetric in the two variables and measurable and bounded. So the image is also in 0, 1. And we call these graphons, like graph functions, and then it's contracted to graphons. Now, given such a graphon and a finite simple graph f, you can define this, which we call the density of f in the graphon w, which is this integral. So what is this integral? That's important. So we assign a variable to each vertex of f, and then for every edge now you have two values. You can evaluate the function w. You take the product over all edges and then integrate it over all the variables from 0 to 1. So here is an example. Let's look at the adjacency matrix of a graph G. Simple, very simple graph. Now, we create a function by sort of replacing, replacing each of these entries by a little square, and the number there should be the value of the function. So this square will have a side of 1 over n, 1/4 in this case. And I'll often use this sort of grayscale notation for a two-variable function. So this function is 0 where it's white and 1 where it's black. That will be convenient. So in this case, this is w sub g, this function associated with the graph. And then if we count the density, or we compute the density of f in this w sub g, it's the same as the density of f in g. Simply because if you assign a variable to each point, then in the product that defines this integral, you need to get a 1 for each edge, which exactly means it must be a homomorphism. And I mean, depending on where the variable falls in this partition, that defines a finite map from the vertex set of f into the vertex set of g. Now I will denote I will call a step function a function for which there's a partition of the unit interval into a finite number of measurable sets, so that if you also partition the other axis in the same way, then on each product set the function is constant. So it's a usual notion of step function, except that it takes the two variables into account. Now step functions correspond to finite graphs with node and edge weights. both node weights and edge weights between 0 and 1. And the node weights sum up to 1. Because if I give you this, I can think of these columns as vertices of a graph, and a square here, say a white square, will mean that there's no edge there, or an edge with weight 0 there. The black square means there's an edge with weight 1 between the corresponding nodes. And the widths of these columns correspond to the node weights. So finite graphs with node and edge weights are sort of correspond to step functions in this setting. Here is another example just to show you that there are also non-step functions which are interesting. And actually this is a little bit of cheating, because this W is bounded but could be negative, but forget about it. So what is the density of f in this W? The two-variable, nice continuous two-variable function. It turns out that it's essentially the number of Eulerian orientations of the graph f. So it's a nice graph theoretic quantity that you get as the density of f in this W. So here is this set that describes the limit objects. And in what sense does it describe the limit object? It describes in the following sense. We say that sequence Gn tends to W if for every graph, simple graph f, the density of f in Gn tends to the density of f in W. So in particular, in this notation, the random graph with edge density a half tends to the half function, identically 1/2 function, because the density of f in the identically 1/2 function is 1/2 to the number of edges, and that's what the density of f in a random graph is. Asymptotically, if there's a little error term coming from the fact that points in homomorphisms may coincide, but generally this is the case. Now here is a quick summary of some of the facts that I will need. So for every convergent graph sequence, there is a graphon, so it's a function, such that which describes the limit, so that Gn tends to this graphon. Conversely, for every graphon, there is a convergent graph sequence that converges to it. So every such measurable function arises as the limit of some sequence. And this limit is essentially unique up to measure-preserving transformation. So these three facts describe exactly, sort of tell you that really this limit behaves as it should. So everything is a limit, and the limit is unique, and so on, up to measure-preserving transformation. Will not be important for it. Now we can use this notion of the graphons to give now a question of what is an extremal graphon problem. And let's make it quite general. You can. So for example, we could say that we maximize some linear combination of densities of certain graphs f, while other linear combinations are bounded. Now this contains all the extremal graph problems I mentioned and many more. Because, for example, if you want to say that something is not a subgraph, excluded subgraph, you just postulate that this is 0. If you fix the density of edges, that's fixing some you can replace it by two inequalities if you wish. And now you can ask, why stop at linear? So why don't I say that let's maximize some polynomial of these numbers, say? But that wouldn't be more general. So the product of two of these, the density of f in W and the density of G in W, is the density of the disjoint union of f and G in W. So you can always linearize such a problem. Good. So far this is Now, here is a related notion. We say that a graphon is finitely forcible if there is a finite number of subgraphs, f1, fm, and prescribed densities alpha 1, alpha m, so that the only graphon that satisfies these is this given w. So that means whenever a graphon U satisfies these equations, it follows that for every f, it's equal to every f has the same density, and then from the general results, it follows that U is essentially the same as W up to some measure preserving transformation, the variable which I don't want to specify more precisely. So this is a finitely forcible graphon. Now, why are we interested in finitely forcible graphons? First of all, every finitely forcible graphon is an extremal graphon. So we just take this sum, and as mentioned before, this can be linearized, and so this gives us an extremal graph problem for which this given finitely forcible graphon is the unique solution. Every extremal graphon, assuming that it's a unique extremal graphon, so we look at all these extremal problems that I mentioned in the introduction have a unique extremum. Now, once the extremum is unique, then of course it's finitely forcible, because fixing all those densities that appear in the problem will actually uniquely define this graphon. And so here is our first unsolved problem. Is it true that every extremal graph problem has a finitely forcible extremal graphon? So what does it mean? Or graphon problem. So we look at an extremal problem. Maybe it has lots of solutions. In general, you may not be able to characterize it in any decent way. But then maybe I add another thing that besides this, that they should have a minimal number of paths of length 3 and a maximum number of paths of length 5 and so on. And adding a finite number of such constraints will now make it unique. I believe that's true, but I don't know how to prove it. Sorry? Without changing the extremal value. Sort of narrow down to a particular extremal graph. I think that's true, but I don't know how to prove it. So finite forcing here is Goodman's theorem, for example, tells you that I quoted about the number of triangles, that if the edge density is 2/3 and the triangle density is 2/9, then it must be this graphon. Of course, when I say, you can always take half of this and put up there. So, you can rearrange the unit interval in a measure-preserving way. But modulo these rearrangements, that's the only solution. Or theorem of Graham, Chung, and Wilson on quasirandom graphs says that if the density of edges in W is a half, say, and the density of 4 cycles is 1/16, then it must be the identical 1/2 function. Now note that here, this does not correspond to a graph, but it sort of corresponds to a large random graph. So that's why in graph theory, this extremal problem has only an asymptotic solution. But once you extend it, it has a nice clean extremal solution, namely the 1/2 function. Now, instead of, first, before forcing a particular graphon, let's look at certain properties that we can force by prescribing a finite number of values, densities. So we call a graphon D regular if its marginal is the constant function D. So integrating one variable, you get the constant function D. So it corresponds to D regular graphs. But in this case, of course, D is between 0 and 1, because that's the way we normalize things. Now, this can be expressed, the regularity, by specifying, first of all, that the edge density is D, and that the density of the complete bipartite graphs with 1 and 2 classes or equivalently paths of length 2 is d squared. Because the density of this you get by taking this integral, squaring it and integrating again, and then Cauchy-Schwarz you must have equality, and then that gives that it's a constant function. So you can express the regularity in this way. Or here is a statement, you recognize it from college. Well, okay, so first I have to explain it. So there is this red dotted line. What does it mean? It means that it's not there. In other words, when I take the integral for a red dotted line, instead of w, I take 1 minus w. So I have a variable for each point, each 3 points, so x1, x2, x3, so it's w x1, x2, w x2, x3 times 1 minus w x1, x3. That, of course, I could expand, so this would be a simple linear combination of real densities, but it's probably... So what does it mean? It means that if this is positive and this is positive, then actually this should be 0. Terrible. This should be 0 here. So the density of this is 0. So the density of this is 0 means that if this is positive and this is positive, then this must be also positive. In fact, it has to be equal to 1. So this means that if w is 0, 1, then this means it's a transitive relation. And of course it's symmetric, so it means that it has these equivalence classes. So in other words, in graph theory terms, it means that the graph is the union of these joint complete graphs. Okay. So what else? This is a little trickier. If I assume that the density of that configuration is 0, now this means that you never find, in finite graph terms, it means that you cannot find two disjoint edges so that these two edges are not there. So two edges where these two are missing. If you think about it, that means that the neighborhoods of points are ordered. If you look at any 2 points, the neighborhood of one of them will contain the neighborhood of the other, and then we can order the neighborhoods by how they contained, and then can prove also that it implies that it's necessarily 0, 1 valued, and so it follows that it looks like this for a function. So you look at the points, the neighborhoods of them are ordered, so for any 2 points, the neighborhood of one contains the neighborhood of the other. It also follows that it's 0, 1 valued, so it looks like this. There is some sort of monotone function and which cuts it into 2 parts, and one half is 1 and the other half is 0. So this property can be expressed as a single density condition. Let me remark here that w is 0, 1 valued cannot be expressed in by a finite number of densities. That's not terribly hard to prove. But I want to make here a remark. If I allowed multiple edges, then I could express it, of course. It's the density of a single edge is equal to the density of double edge is equivalent to saying that it's 0, 1 valued. But I don't want to allow multiple edges because that would create a lot of trouble elsewhere. Among others, the main theorems would not be true that I already quoted. But without multiple edges, there's no way to express that w is 0, 1 valued. Now, there is a theorem that proved with Vera-Schorsch that every step function is finitely forcible. So for every step function, I mean, we have seen that the constant 1/2 function is finitely forcible, and this can be generalize and for every step function find a finite number of density conditions which forces it. And the question is the converse true? Is it true that every finitely forcible function is a step function? We believe that the answer was yes, and we tried very hard to prove it. Now, why is it? So let me give you another motivation why we thought that this was true. And this is sort of building up an analogy with one variable functions. So let's look at also functions which only have one variable. Now here we looked at these subgraph densities, and as I remarked before, for disjoint union it's just multiplicative, so really we may restrict our attention if we want to connected graphs. So let's look at these subgraph densities, and I claim that they are analogous to the moments of the function in the classical sense. Now, in what sense are they analogous? First of all, it is true that the moments of a function determine it up to a measure-preserving transformation. That's also true here. These moments determine the two-variable function up to a measure-preserving transformation. Now, it is also true that these moments are sort of contain independent information in the sense that if I prescribe any k of them, then these are independent, meaning that if you fix these k numbers, k1, km, and you look at the possible moments of a function, they fill a little full-dimensional thing in the k space. And the same is true here. If you take any m of these finite, simple, connected graphs, then these are independent, these moments. That means, again, that they fill a little full-dimensional ball in the M space. So a special case of this was this pink area that you saw about edges versus triangles. That was full-dimensional in the two dimensions. So that's true for any M of these. That's actually fairly old result by Erdős and Joe Spencer and myself from the 70s. Now, you can ask yourself what are the possible sequences. So if for every f, this defines a sequence, a moment sequence, and you can ask what are the possible moment sequences. And there are classical characterizations by Hausdorff and others of these moment sequences. There are various characterizations. They can be characterized by inclusion-exclusion inequalities, by semi-definiteness of certain matrices, and so on. It turns out that all of these characterizations have analogous characterizations. Now, what is the question here? It tells us that I give you a number for every finite graph, and the question is, when do I find a W so that these numbers are the densities of these graphs in the W? And it turns out that there are exactly analogous characterizations analogous to these for this. I don't have time to go into the details, but certainly these exist. Let's go on. If you have a step function in the one variable case, then it's not hard to prove that there is a finite number of moments that determine this function. So that if you fix these moments, then it's only this step function which has these moments. This is also true here, and that was this theorem of Verassos and myself that I quoted, that for every step function you can specify a finite number of these that determine this step function. And now it is also true in the one variable case that if f is not a step function, then for fixing any finite number of moments, there will be a step function with exactly the same moments. So in other words, if it's not a step function, it's it's not determined by its moments because you can actually replace it by a step function which has the same moments. And so we thought that maybe the similar theorem will hold also for two variable functions. Okay, so I told you all the reasons for making the wrong conjecture, because it turns out that the answer is no, and this function here was the first counterexample we found. So this is not a step function because it has steps, but the steps are not rectangles. And it can be forced by these two simple conditions. The first one, I already remarked that this forces it to be like 0, 1 valued and bounded by some monotone arc. And then we can actually force it to be by the second condition. I won't prove it now, but the second condition forces it to be just this function. Now, maybe, okay, so maybe instead of vertical and horizontal straight lines, you have to allow 45-degree lines or something like that. But it turns out that there's a much more general condition here. So we look at a function which looks like this. It is the positive support of a polynomial. So it's 1 where the polynomial is positive and 0 where it's non-positive. Of course, the equality doesn't matter because that's a set of measure 0, so it doesn't matter in these integrations. And this P is a monotone decreasing symmetric polynomial, at least monotone decreasing on the unit square, so in each variable. And then we claim that this is finitely forcible. So for every such polynomial, I can specify a finite number of densities so that the only solution for is this particular function. I would like to sketch the proof of this because it's kind of funny and uses something which is not so very graph theoretic. Sorry? No, this is with Balázs. So now we are with Balázs. So actually, before that, I would like to mention that we believe that the monotone decreasing is just something which we need for the proof. But actually, the support of the positive support of any polynomial should have this property, and probably even something like if you take any polynomial and then you sort of discretize it, you round its values to some finite number of sets that should be finitely forcible. But we have sporadic examples where we can do it, but not in general. But this is a reasonably general class already. So let me give a little sketch of the proof. So first of all, so I already mentioned the fact that it's very nice if I assume that this sort of 2-edge in, 2-edge out 4 cycle, if we exclude it, that already means that the domain is some kind of 0-1 function, and the support of it is bounded by a monotone arc like this, and let's call this set S. Now, of course, we would like to, there is this curve also where the polynomial is 0, and we would like to prove that these two curves, we would like to, not prove, we would like to give a finite number of further conditions which will force this curve, the two curves, to be the same. So the first observation is that let's compute the density of a complete bipartite graph in W. Now, so that means that I have to map both color classes, and let's just think that of one color class is mapped onto one side and the other color class mapped onto the other side. So we have A points here and B points here. Now when we want that all these intersection points, so all points with these coordinates, they are edges in here, so they should be non-zero here. But there's only one which matters. It's the largest point versus the largest point. If that is in the black domain, then all the others are in the black domain. So we can integrate xy is this largest point, and there are x to the a minus 1 sort of is the measure of the choices for all the smaller ones, and y to the b minus 1 is the choices for all the other ones. And you have an AB because you can pick which one should be the largest. There's A times B ways of picking this. So you get this integral. But now you rewrite this integral by Stokes' formula as an integration over the boundary of something here. This is the normal vector and appropriate coordinate. Now we write up this thing here with trying to interchange the role of x and y, and then average is just some minor things. So eventually you get that if you integrate x to the a, y to the b times some stuff here, this is the sum of the two coordinates of the normal vector over the boundary, then this can be expressed as some linear combination of subgraph densities. But now from this, let's look at this more complicated expression, x times y times this polynomial that we want to integrate squared times this normal vector, sum of the normal vectors, coordinates of the normal vectors. This can be written as a linear combination of subgraph densities because the polynomial is a linear, this is a polynomial here, and it's a linear combination of terms of this type. So what does this mean? It means that if I plug in here the real w that I want to actually get, then the left-hand side will be 0, because on the boundary either x is 0 or y is 0 or pxy is 0. These are the three parts of the boundary. But that means that if I plug in this u, which sort of mimics w in all these densities, there's a finite number of densities that I have here, plugging in that u, I would get the same formula. So I must have 0 here. In particular, I must have 0 while now this is all non-negative on the boundary, so I must have 0 while I am integrating along the curve, which means that this everything else is positive there, so pxy must be 0 on that curve, so which means that we must have this particular polynomial. So this is a kind of funny proof, and I think that without the monotonicity, trouble is that one gets into high dimensional Stokes, and we got lost in the combinatorics of it, but possibly it's doable.
Where did you use the monotonicity?
Oh, I need that this stays positive, which means that it's a little bit less than monotonicity, but the normal vector, the sum of the coordinates of the normal vector must stay positive. Using it here. Also, actually, more importantly here, and this might be fudged somehow, but more importantly here, because that I said that it's enough to pick the largest point representing one color class and the largest point representing the other color class. And if that point falls into the black domain, then everything else falls into the black domain. That's not true once it's not monotone. I don't know how to watch this. Here is a very interesting question. Is this graphon finitely forcible? Now here, instead of the 0, 1 interval, we take we can always replace the 0, 1 interval by any other probability space. And so here we take a probability space as the surface of a ball, a uniform distribution on it, and you connect two of them if the angle is less than pi over 2. I think it is finitely forcible, but I don't know how to do it. It looks. Now, one reason is that Nati believes there is a famous unsolved extremal graph problem, which is what is the minimum number of complete and empty foregraphs in a graph. So you count the number of complete foregraphs in the graph and the number of complete foregraphs in the complement. Take the sum. Erdős conjectured that the random graph would give the minimum, but that was disproved by Andrew Thomason. So it is known that there are graphs but the extremal which have a smaller number of complete foregraphs plus empty foregraphs, and it's a tantalizing unsolved problem to know what is the minimum, which graphs give the minimum. So this is a very long-standing extremal graph problem, and I think Nati worked on it, and he developed the idea that the extremal graph must look something like that. Not this one, but it's some kind of sphere where the distance, when the connection is depending on the distance. And so at least it would be nice to know if this kind of graphs actually can occur as extremal graphs. There's one more interesting class of graphs where finite forcing seems to behave in an interesting way. These are union complement graphs, sometimes also called Cographs, which I think is a bad name because it looks like they are duals of graphs. But this is just a special class of graphs. They are constructed from a single node by the operation taking disjoint union and complementation. So, and there's a theorem which characterizes them, which says that a union complement graph has no induced path on 4 points and vice versa. So, in other words, these graphs can be characterized they can be finitely described, namely the graphs which have no P4. So, by this condition. You get each of these graphs can be described by a tree. So you take, say, here 3 single nodes, take the union and complement it. You get this into a triangle. You take another single node, take the union and complement it. You get the claw, I think, and so on. So each of the endpoints or leaves correspond to a single node, and each internal node, meaning take the union of all the descendants and complement it. Now you can define a UC graphon, which is just by this property that there is no induced path of length 3. And again, you can describe these, it can be proved that you can describe these by a tree, an infinite tree, where you have a probability measure on infinite paths. So yes?
By the dotted lines and
here? Oh, it's the old thing that you have to take the product of W over 3 edges and the product of 1 minus W over the other 3 edges. And then it can be shown that this implies that W is 0, 1 valued, and therefore it's can be thought of as a graph on a possibly infinite or even uncountable set. And here is a description of it. you can take a probability measure on the paths of this infinite tree, on the end, sort of on the ends, and now take 2 points. They are 2 paths. They meet somewhere, and if this meeting point is at an even distance from the root, then we connect them, and if they are at an odd distance from the root, then we don't connect them, and that defines this graph. And that extends the finite definition. So these are these graphons. Now, why are they interesting? I don't know whether they are interesting, but they seem to be interesting. First of all, if the graphon is a step function if and only if this tree is finite. It's not a big deal. Now, we are interested in graphons which are regular in the sense that they integrate in every integrate out one variable, it becomes a constant function. So every regular graphon is locally finite. Conversely, if I give you a locally finite tree with all the degrees at least 2, then there is a unique regular UC graphon that with this tree. So somehow these are indexed by this correspondence by the one-to-one correspondence with these trees, these regular UC graphons. Now, if such a subfunction, if such a UC graphon is a step function, a regular UC graphon is a step function, then it turns out that its degree is a rational number. On the other hand, for every real D, you can find a UC graphon with an infinite tree, which is D regular, even if D is irrational. So this implies now that if you look at these 3 conditions, the density of induced path is 0, the edge density is 1 over root 2, and the density of path on 3 nodes is 1/2, so it's the square of this. So these 2 together imply that it's 1 over root 2 regular, and that's an irrational number, so it cannot be a step function. So this is perhaps the simplest example where you have some of these specified value, or one of the simplest examples, which is not a step function. In fact, if you the construction that it is satisfiable, so there is a W like this, and it gives a rather fractal-like picture if you actually work it out. Now, so this which kind of functions can be forced by a finite number of densities is open, and I don't even have a conjecture for it. I mentioned a few conjectures here, but I think it's an extremely interesting problem. So to mention a couple of, well, okay, so I'm done with just one more result. So what is not finitely forcible? So here is an example. If this is a polynomial, then it is not finitely forcible. So remember, if it's the support of a polynomial, so another a polynomial rounded to 0 and 1, it's finitely forcible. But the polynomial itself, we can prove, is not finitely forcible. And in fact, we don't have any single example of a finitely forcible, say, continuous function. So in fact, it might be true that every finitely forcible function has a finite range. So it assumes only a finite number of values. It can have arbitrary many values because step functions are all finitely forcible. So it means that even though it's not necessarily a step function in our sense, it's a step function in a weaker sense. That instead of dividing the 0-1 interval into measurable sets, you just divide the square into a finite number of measurable sets, and it should be constant on each of those. So that looks like a reasonable conjecture in this direction, and Well, that's all I know about this problem. Question there?
What if you wanted to study extremal properties beyond just, let's say, for induced subgraphs, rather, let's say, the sort of minors or sort of homeomorphic, sort of graphs that are homeomorphic to some sub? Is this framework general enough to do that?
No, this framework is not. It's that's one of the possible sort of open directions to. Basically, we look at here one category of graphs, so to say. So one notion of mapping one graph into another, and built on this, we get this notion of convergence, and we get the notion of limits. It's completely plausible that there are analogous theories, for example, for minors, because exactly the main theorems on minors, Robertson-Seymour, Thomas, they have this flavor that if you have a very large graph, if you exclude a minor and you have a very large graph, then it must look like more or less a finite number of surfaces with a little disturbance added. So a possible statement would be that in the limit, where I don't know what it means, but in the limit, this should be like a surface, or maybe it should be a surface. I don't know how to make this. But the theorems have very much this flavor that they describe you what in the limit, say, a graph without a K5 minor must look like. K5 minor is okay. That's planar, but K6 minor.
Just for the quantitative aspect, so for in the one variable case, a function with k values is determined by 2k moments. So what is the quantitative analog variable?
Well, that's where, that was the first problem. If you go back to this picture, these graphs, the red dots here, complete multipartite graphs, they are determined by edge and triangle densities. So they are determined by two moments uniquely. Now in the opposite direction, if for the positive, so every step function can be determined by a finite number of moments. In fact, we have a bound that if it has k steps, then maybe k to the 2k moments or some k to the 10k moments. So some bound in terms of k, but a large number of them. And I don't know what the truth is. Joel Spencer has a little bit sharper bounds, but they are still exponential in k. Thank you.